Hi, Nesta. How you doing? In an exit meeting, wrapping up. So soon come to you here.
No problem.
Okay. Good afternoon, guys. I so apologize for the delay. Had an exit meeting that ended after 5 o'clock, and I was just very tired, truth be told. So I am coming to your class a tired teacher. So forgive me. But how are you though? Otherwise, are you guys okay?
Good evening, sir.
Hey, Sean, what's up? How are you?
I'm okay, sir.
Nice. All right. Where were we the last time again?
Repeat, sir.
Where were we the last time again? We finished differentiation, applications of differentiation. We are now into applications of integration. And I'm just trying to remember, what was the last thing we did, guys? Please, somebody help me. Did we start the trapezoidal rule?
No, sir. No, sir.
So the MVT thing, I think we were doing.
Oh, okay, thank you, thank you. We look at the mean value theorem for differentiation and that for integration. Very good. All right, so having gone through those, I then want to, okay, now remember, so I had given you one to do and find the mean value. I think this is where we ended. I only had my answer on and didn't have the solution to it. I know Sash was asking about the solution, so I sat up after class and did the solution. So just allow me to go through this as a refresher before we move into our trapezoidal rule. Based on how things are going and the time that has passed, I'm going to start and finish trapezoidal today. So I'm going to spend about no more than about 15 minutes on, no more than 10 minutes on the solution. And then we just move into, oh Lord. All right, there it goes again. So the question said, find the values of C, the values of C that satisfy the mean value theorem for integrals on 0, 1 for the function x times 1 minus x. Now, it did say integration. It did say integration. Now, there is a rule that speaks about integration by parts. And as I continue to prepare notes for you, that thing bothered me for quite a while. Because I'm there trying to write questions for you. And I write questions, I'm going to reach to the final part now for integration after though, and I'm speaking specifically on differential equations. when I reach a particular point, it is asking me to solve the integration, to do the integration by parts. And I'm looking to see if integration by parts is on your syllabus, and I'm not finding it. So I have to abandon those questions. So because you're not doing integration by parts, when you get a question like this, okay, sounds like they're fucking. When you get a question like this, best believe that you have to expand. X times 1 is x, and x times negative x is negative x squared. So you recognize that. I just recognize it. That there's some additional stuff to be placed up top here, so right? I have not done the first part of it up here. I got this question, I got this partial answer from you guys in class last Thursday. Anybody remember? You were the ones who gave me that? Want to talk to me now?
I don't remember, sir.
No, man. Remember, I have not done
Yes,
it.
sir. Yes, sir.
Right.
We gave you that.
Yeah, they gave me this Ryan, because what I did was just to I just projected my answer, and they gave me this equation, and then I worked it from here. So I never did the integration at all, because remember, you have to integrate it for the values. Oh no. See the run, I never did this part.
Okay, sir.
So this is going to become x minus x squared dx. When I integrate x, what do I get?
One. Okay.
What? When I integrate x squared, what do I get?
2x.
There is x cube.
When I integrate x, what do I get?
X square over
X
2.
square over 2.
Right, thank you, please. So tell me the correct stuff. You tell me something. Sure. So when I integrate x, so remember, I have to integrate the function. Remember, this is a formulation. The integral of a function over b minus a. Right? So it's all of that over b minus a. So what I'm doing now is just integrating the function first, and then I'm going to do the division. So b a see my b here, see my a here, and my f of x is this dx. See here, my b, my a, my f of x and dx. So I'm now expanding. X times 1 is x. X times negative x is negative x squares. When I integrate x, I'm going to get x squared over 2. When I integrate x squared, I'm going to get x cubed over 3. And these are my limits, 1, 0. So I'm going to know 1, 0. If I had remembered this, I'd have done it from last class because I did the other part last time around. But I honestly didn't remember the last part, that part. So forgive me. But it's a good thing because it gives you guys an opportunity to see what I'm doing here now. So this is it. So when I integrate, I'm then going to be applying my upper limit and my lower limit. Remember, it's always upper limit minus lower limit. It is always my upper limit minus my lower limit. So I'm substituting my upper limit into the function, and then I'm subtracting my lower limit from it. Let me see them question here now. What if I mark them carry now? Or what if I work have to do? Tell me if you agree with that.
Yes, sir.
Thank you, Sean. And then my LCM is going to be 6, and 2 into 6 goes 3 times, and 3 times 1 is 3. 3 into 6 goes 2 times, and 2 times negative 1 is negative 2. Oh, you know, somebody need to ask a question, but anyhow, let's go to the school business first, which is going to be equal to 1 over 6. And that is equal to 1 over 6, all right? Now, that's just my partial answer. So now I need to do b minus a, but b minus a is 1 minus 0. And 1 minus 0 is 1. So I'm going to have 1 over 6 divided by 1, which is equals to 1 over 6. Now, so that's going to have 1 over 6, all right? And then now, since I have 1 over 6, remember now, it is f of c that is equals to all of that. It is f of c that is equals to all of that. So it now becomes, I now need to find f of c. So f of c is anywhere in f I see x, I put c. So it now becomes c times 1 minus c, which is c minus c squared. See here? C minus c squares, and that is going to be equal to this 1/6. And then now, this is where the calculation continues from now. All right? So what I'm doing, by the way, I sense it in my spirit. Are you all following me?
Yes, sir.
The C.
Yes, sir.
Sasha, here you're coming in. Okay, Sean, I hear you. But Sasha, here coming in.
So I'm on the road, but I'm saying I'm confused about the c square minus whatever equal 1 over 6.
Okay, but remember you, I think you are one of them who gave me. Well, I know you asked me how I arrive at the answer, but I know, all right. So this is, don't worry about that. But do you understand, Sash, the 1/6, how I got the 1/6?
Yes, sir. Yes.
All right, good. All right. So just tune in, please. Hold on for yourself. Don't want to make them take it from your ear or hurt you. But watch this. Or make the tire wheel run over it. Watch this. Copy. Now, bam implies paste again. F of C equals to 1/6. Look at this now. So I'm going back to my original question, which is f of x is equal to x times 1 minus x. Implies that my f of c, anywhere in f of x I see x, I put c. So I'm going to have c times from here. Anywhere I see x, I put c. So it's c times 1 minus c. See it right here, so? But remember, f of x is equals, f of c is equal to 1/6. F of c is equal to 1/6. So how do you know that? Because when I'm using the mean value theorem, what I'm evaluating is actually f of c. See it here, so? I'm actually evaluating f of c. So it's going to be the integral over b minus a, and that gives my f of c. So since I have two f of c's, and the f of c's are the same, I'm going to equate them. So that's why I equate. I'm going to equate, and I get c times 1 is c, and c times negative c is negative c squares equals to 1/6. So f of c is equals to c times 1 minus c, but f of c is also equals to 1/6. So when I equate these two, I get rid of f of c, and then I just have my function in c, which is this. C times c minus c squared over equal 1/6. So what I'm doing here now, I'm multiplying through by -1. So I'm going to get positive c squared, negative c, and this is going to become this is going to be a positive 1/6. Right over here,
Sir, question, why you use the -1 though?
because I don't want a negative c squares.
Okay, all right.
Right? Good question. I'm factorizing, and I don't want a negative c squares. I want my c squared to be positive. So that's why, and I'm only able to multiply through by -1 because it's an equation. Had it been an expression, we can't dog, right? But good question. I only multiply through by c squared because, I mean -1, because I have a negative c squares and I don't want a negative c squares. All right. So you see better here now. What I did was to subtract 1/6 from both sides. I subtracted 1/6 from both sides. So what I'm going to have is, c minus c squared minus -1/6 equals 0. When I multiply through by -1, to get rid of the negative sign in front of the c squares, I'm going to have a positive c squares and negative c. And this is a -1/6. It now becomes a positive 1/6 equals 0. Using the quadratic formula, that's very wrong. I type it and I felt it. Using the quadratic formula, I'm going to have x is equal to -b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So why are you using that? Because I can't factorize this. There are no real factors for it. So I have to use the quadratic formula because I'm solving for c now, you know. That's the point. When you do the mean value theorem, you're solving for c. So what is going to happen now? My a is a coefficient of x squared, sorry, c squares in this case, which is 1. My b is a coefficient of c, in this case is -1. And my c is a constant. In this case is going to be positive 1/6 right here. So all I'm doing here now, anywhere into my quadratic formula, I see the value a, b, and c. I'm going to substitute all of these here. So x is equal to -b, x is equal to minus and -b, right here, so. plus or minus the square root of b squared, so it's going to be -1 squared, minus 4 times a, which is 1, times c, which is 1/6, all over 2 times a, so it's all over 2 times 1. And -1 times 1 is going to be 1, plus or minus, watch me now. -1 squared is +1. And -4 times 1 is -4, times 1/6 is -4/6. -4/6, and 2 times 1 is 2. And we have 1, that 1, plus or minus. 1 minus 4/6 is the same thing as 1/3. Oh, you know that, sir? Let me just show you a piece here. Let me put it in a different color. This is side work. Side work. So that's side work. So this one I'm calling 6/6. That one I'm calling 6/6. 6/6. Once the denominators are the same, I'll go ahead and I subtract the numerator and put back the denominator. Once the denominators are the same, I subtract, do the operation, and put back the denominator. So the denominators are the same. So I'm keeping the denominator and subtracting the numerator. So give me 6 minus 4. And 6 minus 4 is 2. 6 minus 4 is 2. So I'm going to have 2/6. And 2/6 is the same thing as 1/3. So I'm just doing it in stages so you can see. So all that I have here is a side work, jumping from here to here. But sir, we just put on the calculator 1 minus 4/6 and I got my 1/3. Fine. Hooray for you. But I'm just showing you a little bit more mathematics here to say, once you're doing a fraction and the denominators are the same, I keep the denominator and do the operation for the numerator. All right, but what I'm doing is to make this one an equivalent fraction first. I make one an equivalent fraction first. All right. Okay, Ryan, I hear you. Hey, Ryan, charge your phone for not using a box. And you know also traffic stay with you already.
Meeting all day, boss. Sorry.
All right, never mind, Papa. Understand the struggles. I mean, I was in a meeting that ended after 5 o'clock and I have a class at 5. Anyhow, struggles real. It pays the bills, so I'm not complaining. All right. So I'm gonna have my 1/3, my positive 1/3, and then this is what I'm gonna do now. So look at what happened. Just as how I separated, I put everything on a one denominator here, 6. I can now separate it. This 1 is over the 2, and so is the root of 1/3 is over the 2. So I'm separating it and calling it 1/2 plus or minus 1/3 over 2. All right, 1/3 over 2. Work with me now. Remember, when you're dividing two fractions, you're going to invert and multiply. What I did here first was to rationalize. Oh, I think I showed you the rationalization here. No, I didn't. I'm just showing you something here. Watch me. Please note. This root of 1 over 3 is the same thing as the root of 1 divided by the root of 3. Is the same thing as the root of 1 divided by the root of 3. So the root of 1/3, it means that everything under here The numerator is being square rooted as well as the denominator. That's what it means. The numerator is being square rooted as well as the denominator. So when I square root the numerator, I'm going to get the root of 1 over the root of 3. Now the root of 1 is the same thing as 1. And then I keep the root of 3. And then I'm going to have it as 2 over 1. All right? Now look at what happens here. When I'm dividing two fractions, I invert and multiply. So 1 over the root of 3 is this 1 over the root of 3. And this 2 over 1 now becomes 1 over 2. Hey, Papa. Becomes 1 over 2. Now I need to rationalize. Right? I'm not rationalizing. So why do you have to rationalize? We never normally leave a square root sign in the denominator. It's unacceptable. We never normally leave a square root sign in the denominator. So because I have the square root sign in the denominator here, I have to rationalize. How do you rationalize, sir? Watch it. I highlighted it in blue. I'm multiplying both the numerator and the denominator by the root of 3. I'm going to ask you the question. What is the significance of multiplying the numerator and denominator by root over 3 divided by root over 3? Tell me what the significance of this. What is this? What is the root of 3 over the root of 3? What is the root of 3 over the root of 3? Next one. What is the root of 3 divided by the root of 3? Okay.
One, sir.
Duh. The same thing in the numerator is the same thing in the denominator. So it has to be 1. Now tell me, when I multiply something by 1, what is the significance of that? When I multiply something by 1, what is it? What is the significance of that? What is 1 times 2?
2, sir.
What is 1 times 3?
3.
Okay, so what are you saying? What's the significance of when I multiply by 1?
To get back the same number, sir.
I'm going to get back the same thing, right? So the significance of all of this is I'm not changing this root of 1 over the root of 3. I'm not changing. So when I rationalize, I am not changing the stuff. I'm only writing it in a different form. I'm not changing it. I'm only writing it in a different form. Very important for you to remember. Not change it. I'm only writing it in a different form. All right? So I'm going to multiply the root of 3 by 1 to give me the root of 3. And the root of 3 divided by, the root of 3 times the root of 3 is going to be 3. When I multiply the root of 3 by the root of 3, I'm going to get 3. See down here, so? I'm going to get 3. And 1 times the root of 3 is the root of 3. And then I still have the half to multiply it by. So the root of 3 times 1 is the root of 3. And 3 times 2 is 6. So this is how I ended up now with my final answer as C equals 1/2 plus or minus the root of 3 over 6. Sir, the question long, me agree. Sir, them can give something like this in the exam, what to top them. Absolutely. Absolutely. So you have to be very mindful of what is happening right here. You have to be very mindful of it. All right, any questions? I'm leaving all these side notes there so you can see what is happening. Talk to me, guys.
No, sir.
You good? All right.
Yes, sir.
I must move into the trapezoidal rule. I must move into the trapezoidal rule. Now, one of the things you will learn about me is I try to be a fair person. So if we can, hey, Mr. Fraser, a long time I don't see you, know. Oh, well, go on. Are you okay, Ramesh? It's long time I don't see you.
Sir, I direct message. Good evening.
Yeah, man. Yes, Papa. I saw your message, Papa.
Sir, never really have light from over there.
Oh, no, man. I hope you're accessing the notes and edits
Yes,
and
sir.
everything. Because I have not seen you for quite a number of days, consecutive days too. All right. Where was I going now? Jesus, I was going to go somewhere. Where was I going to go, Lord? Oh yeah. So one of the things you'll know about me. So if Aviana, I'm troubling Aviana today. If Aviana and I are okay, no problem. Yeah, man, it's there. But I'll link me afterwards. Let me trouble Aviana. Oh, let me tell you what is happening. I uploaded the recordings, you know. And when I went back to check on something, I see where them tell me that 2 of the calculus 2 failed. And I don't know which 2 of them failed. But anyhow, you can look and tell me so I can go back and guesstimate the dates because I don't get the recordings the same time. So like after class, the recordings don't come to me. And sometimes it takes a couple of days to come to me. So help me out in that regard so I can just go back into the email and guesstimate when it is. All right. So I know I have 2 or maybe 3. I think there are like about 4 of them that failed, but I think 3 of them was calculus 2 and 1 of them was my Cape math. Avi, this is your teacher troubling you know. Am I allowed to trouble you, Aviana? Please say yes.
Yes, sir.
Okay, good. Thank you. That's why I love you so much. All right. So one of the things that I'm going to tell you, Aviana and I are very good friends. But if Aviana does something, we're going to set her straight. Aviana, you did something and I didn't appreciate it. You know what with Sir Shanda afterwards? If Aviana want to vex me in a fair business, but I am going to move on. Aviana, who are you? If you don't want to answer me, that's your business. Me, I make it right with God. So I don't hold up people. Why am I going there? I'm going there because when I speak the truth, I am set free. Hear the truth. Just as how I know you guys know how to differentiate, I know that you guys know how to also integrate. And it's not asking you, it's telling you. I know you guys. Yes, mommy. I know you guys can integrate. If I couldn't, I'd have told you. I am just like that. Like me or don't like me. So I know you know how to integrate. You may not remember all the steps of the integration. And that, in that regard, I would say to you, go back to your calculus 1 and review those integrations, the different techniques. But I know that you know how to integrate. So with that said, I'm congratulating you. I'm congratulating you. The trapezoidal rule is going to be an approximation to determine the area beneath a curve. So we're not actually doing the integration, but we're doing this approximation, which is a rule, a trapezoidal rule, right? By creating many trapezoids to approximate the area under the curve. The man may, however, say to you, Edo, do the actual calculation and then calculate the percentage error, the something. Let me give you an example. I remember one of my first days being placed, being placed on the cash line, the teller line, when I was in another area of my professional life. You know, the rookie get the worst job to do. Not because you think you're bright, you can go in there and go do the work with the people that might do for you 3, 4, 5, 6, 7, 10 years. And you just come in, you're going to do the work but nobody no want to do. So the man then give me some $20 coins at the time to count out. Bag of coins coming from BOG, and it's so top. Me, good me, must stand up and count out them $20 coin. Me not like you, man. I beg, so till. Anyhow, so I placed a coin on the table and I was counting the coins and I remember a supervisor came over to me and said, you know, that is tedious and your hand will hurt you. Me said, going to hurt me, start hurt me already. And the supervisor come and said, all right, come here, let me show you an easy way. And I said, what is it? And she took out a little scale and she said, you're bagging them in $500 portion. You count out $500 and you get the weight. Approximately, this supposed to be the weight. I said, okay, fine. I said, I can work with that. So what's the point? Each $20 coin should have the same weight. And you notice I'm using an operative should, but sometimes they don't. But when I'm weighing out, say, $500 worth of $20 coins, right? Which would be 25 of them or whatever it is, whatever parcel I'm doing. I may have one of the $20 coin that comes up a little bit more in weight or a little bit less. So the actual weight of the $20 coin, say, is supposed to be 12 ounces for argument's sake. I may get 12.75 ounces, right? In a case like that, I may have to count out that batch again because 12.75 is just way too far from the 12 ounces. If I get 12.2 ounces or 12.3 ounces, I can say, okay, this is it. So that is an approximation. Now, if I get a bag of coins from the bank and I parcel them out so that the tellers can each get their parcel of coins, when I finish parcel of the coins, everything's supposed to add back up. If them don't add back up, you know, we have to go back through the bags and count them out. You understand? So I didn't like that at all. I mean, I was really glad when they graduated me from that something. What's the point? Approximation. Approximation comes in very handy when you are doing work. We're working smart and not hard. All right. So this technique is a much more accurate way of approximating area beneath a curve. To construct the trapezoids, you mark the height of the function at the beginning and the end of the width interval. Then connect the 2 points. However, this method requires you to memorize a formula. And everything comes with teething pains. And as I said to you before, every single thing that you do for this course has a formulation. So I would suspect by now that you guys would have already gotten your flashcards. And you have written down the formulations for all the flash. Remember, you're doing a face-to-face exam, you know. Saying that we ain't having the resources with you, you're doing a face-to-face exam. And having gone through online for 2 years, for your second year of the associates, and no, for the last part of your first year, to all of your second year, and to piece of your third year, you have to now get back into the groove of memorizing these stuff. Get your cue cards. Everything that we do, we have formulation, all right? So this is what it is that we're talking about. I'm going to let f of x, I'm going to let f be continuous. I'm going to let f be continuous. I'm going to let f be continuous on the interval a comma b. It's going to be continuous on the interval a comma b. The trapezoidal rule for approximating the function f of x dx to my upper limit b, my lower limit a. This is what I'm going to have. It looks ugly, but I'm going to walk you through it. It's really not difficult. I don't want anybody to blink, because if you do, you're going to miss it. big fan for Sash because I know she the road. So this is it. This is my function. See here? F of x dx, my upper limit, my lower limit. This formulation is something that you know from calculus 1. That formulation is something that you know from calculus 1. All right? This is a formulation that we're going to be using to approximate the stuff. I want you to pay attention because I'm going to work an example with you. So it is that you can see what is happening. Function f of x dx, my upper limit b, my lower limit a. This is what we're going to be doing. We're going to be finding the change in x over 2. How do we find the change in x, sir? Delta x, that is. Delta x is going to be b minus a over n. N, what is n? N will be the number of trapezoids. Sir, I don't understand what you mean by trapezoids. Okay, no problem. I'll soon explain it to you. So my delta x is going to be b minus a over n. What is b, sir? Oh, I see it, sir, the upper limit, right? Yes. And a is going to be my lower limit. N will be the number of trapezoids. Oh, so sir, that means the question will tell you how many trapezoids to use? Absolutely. Then, sir, no easy. We think so too. Right? So they will tell you how many trapezoids. Evaluate this using this number of trapezoids. So you know what your n is, you will know what your b is, you'll know what your a is. So delta x you can find. When you find your delta x, you're going to divide it by 2. Watch me and watch me closely. Don't blink. Ryan, keep your eyes on the road. Sash, hold your handbag. You see the first term and the last term, I polarize those in blue, because every other term is going to be doubled. You see, the second term is 2 times f of x1, then 2 times f of x2, then 2 times f of x3, and a sort of galang, 2 times f of xn plus 1. But when you reach the last term, you now go multiply by 2. And when you reach the first term, you now multiply by 2. So the first 2 terms are not multiplied by 2, but every other term is going to be multiplied by 2. Let me say that one more time, because that is very important. Very, very important. In applying the formulation, you are going to be finding f of 0, f of x of 0. The first term and the last term, fx subscript n, will not be multiplied by 2, but every other term will be doubled. Some teachers do it differently and put a 2 outside and then put all of these in parentheses so that we have 2 sets of brackets. I don't do it that way, because I want students to know, say, every term them get, with the exception of the first one and the last one, supposed to be multiplied by 2. All right? Where delta x is used to find the width of the trapezoid. So this delta x here, so, is me finding the width of the trapezoid. So put it this way. Put it this way. And I want you to work with me. I like using real life to explain the mathematics, because maths is life. If you have, like I had earlier when I was feeling a little overwhelmed, I say, you know what? Let me go drink a Dr. Pepper. I like my Dr. Pepper very cold. So I took some ice from the refrigerator, the cubes, and put in the cup and pour the soda on top of it. Hold that thought. If I were to crush my ice this time around and throw the soda on top of it, which of the 2 containers, 2 cups, will the ice melt faster? The crushed ice or the cube ice?
Crush ice will melt faster.
Yes, sir.
Why? Why can the crushed ice melt faster?
Because it's in smaller pieces, so it's easier.
Very good. And you are correct. You are correct. If I was in another setting, I'll say the rate of
Surface
reaction.
area.
Say it again.
No, I'm saying the surface area is much smaller.
Woo! You can know who did chemistry now. So when I increase the surface area, it means that the rate of the reaction goes faster. Real talk. Real talk. This is mathematics. So when I have a larger number of trapezoids, it means that my approximation will get very closer to the actual integral. So the greater the number of trapezoids I use, the closer I will get to my actual answer. Remember, these are just approximations, They are just approximations. But when I increase the number of trapezoids, I am going to increase the likelihood of me getting my answer very, 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 very close. Very close. When I use a small number of trapezoids, chances are I'm going to be having errors in my calculation. My calculation is going to be a little bit off, sometimes a whole heap off. All right, very good. I'm happy that you catch on to that. So B is going to be the upper limit and A is the lower limit. Duh, you know this. The area of any trapezoid is half the sum of the parallel sides times the perpendicular height. So this is something that you should know from little school. So when you're calculating the area of a trapezoid, A is going to be half AB times H, half the sum of the parallel sides times the perpendicular height. All right? The reason you will use those tools in the trapezoid rule is that every base is used twice for consecutive trapezoids, except for the bases at the endpoints. Except for the bases at the endpoints. So every base is going to be used twice in the trapezoid away from the endpoints. The first one and the last one. Note, the trapezoidal rule overestimates a curve that is concave up, but underestimates the function that are concave down. All right? So it overestimates when it is concave up, but underestimate when it's concave down. Watch this. Which one is this? Is this concave up or concave down?
Up. Wait, that would be down.
Very good. So this one will be, this one here is underestimating the function that is concave down. So this is concave down. So you see this little airspace right here. So it means say me now get the actual approximation right here, so because this is concave down. So I'm missing this area right here, so I'm not accounting for it. But when my something concave up, like in this piece here, and even this small piece right here, so it means that I'm overestimating right here. See here? The trapezoidal rule overestimates a curve that is concave up. So the curve concave up right here, so not as, this is not as up as this one, if you understand what I mean. All right. This is more like the point of inflection. So you don't have as much concave taking place right here. But because here is concave in up, right here, so it means that I'm going to be overestimating. This one I'm underestimating. So what the trapezoidal is saying is that when something concave down and I underestimate, the other areas that concave up will compensate for this area that I am not accounting for. Can you see that?
Yes, sir.
Yes,
Yeah,
sir.
man. So
Repeat that, sir. I didn't get.
no, but I'm saying to you, in circumstances where it is concaving down and I'm underestimating, the areas that are overestimating, that little piece right here, so and this little piece right here, I can use it to account for the missing area right here. So the areas that I'm overestimating will be used to compensate the area that is underestimated. Can you see that?
Yes, sir. Okay.
Yeah, man. All right, good. I'm explaining the whole business of the trapezoidal. I don't start with a question yet. I'm only explaining. Trapezoidal is very nice. I mean, you're going to love it. I promise you. All right, so it says the area of the trapezoidal, the shaded region, approximately equals the area bounded by y equals f of x. See the curve here? Me telling you it's going to be y equal f of x. So look at what we're going to be doing now. Each of these things are called my trapezoids. So I'm going to have my trapezoid. I'm going to have 1, 2, 3 trapezoids. Can you see that?
Sir.
All right. I want you to be very active in class today, you know. I want you to be very active in class today. I want you to put up 4 fingers. Hold up one of your hands. Rest your thumb into the palm of your hands for me. I want everybody to do this because when I tell you this one time and you catch it, my problems are solved. So put your thumb into the middle of your palm and hold up your 4 fingers. Your index, your middle, your ring, and your pinky winky. All right? Then the other hand, I want you to put between fingers and tell me how many times you can put it between fingers. Answer.
1.
3, sir.
3 times. Look at it again, Charles. You have 4 fingers up.
Sir, it's not me.
Sorry, who said that? Who said that a while ago then? Sorry.
Me, sir.
Oh, okay. Sorry, Charles. So I have 3 spaces that I can remove and put my fingers there. Each of those spaces is representing a trapezoid. Each of those spaces is representing a trapezoid. Watch me. Look at it. This is 1 finger, 2 fingers, 3 fingers, 4 fingers. Between finger 1 and finger 2 is a trapezoid. Between 2 and 3 is a trapezoid. Between 3 and 4 is a trapezoid. So you see why this one here have 2? Because right here, so this here finger is going to have a base right here, so I'm going to have a base over this side. Talk truth.
Yes, sir.
Yes, sir.
Yes,
The one here does going to have 1 base, don't it?
Yes, sir.
And the one here does going to have 1 base, but the one here will have a base to the left and to the right. This it mean back up here, so the first one got only 1 base because it don't have nothing to the left, right? The last one will have 1 base because it don't have nothing to the right. So the endpoints only have 1 base, but the ones in betwixt them will have 2 bases. The one here will have a base from the side here, it will have a base from the side. And guess what? My trapezoids are going to be equidistant. My trapezoids are going to be equidistant, meaning equal distant. So the same base that is going to be right here, so is going to be the same base that is going to be right here, so. Hence my 2 right here, so. Are you following me so far? You can put your hands down. I don't know if anybody's still holding their 4 fingers. But anyhow, are you following me?
Yes, sir.
Am I making sense? Am I making any sense?
Yes, sir.
All right. No, let me tell you something. So I was in an exit meeting today. And I tell you, say, we run to the supermarket, go buy some Dr. Pepper. Come to kind of just one little boost up energy for my classes in the night there. And as I got into the supermarket, principal asked a question. Mr. Shand, how the online business working? I said, well, sir, I can tell you. My calculus 2 students tell me, say, they want online. But what are the performances? I said, sir, they're performing well. You cannot fail me. That's the point I'm making. You cannot fail me. But one of the things that I can tell you as a fact, I don't know if it is that your spatial awareness has developed in this online medium, online teaching and learning, situation that we face ourselves in, or maybe because of the examples, the real life examples that I'm utilizing. But I find that the class is getting the stuff through this medium. And for that, I congratulate you. Now, let me hasten to say that I'm very aware that it may not be everybody who is seeing it at the same time. those of you who are so challenged and don't want to speak up in class because you don't want nobody to look down on you, speak to me. Reach out to me and say, sir, you know, you're explaining something about the four fingers and I don't see it. Call me. Make we convert the call to a video so we can show you. Yes, go ahead.
I'm not to try to what you but my sorry, I'm positive. Gave us some negative. Not in a negativity, sorry. But I find the topic more difficult when I cannot relate it to something in real life. So you see, if you show me that and you say, for example, when a car drive back way and something a minus bit, so if I can't relate it to something real in life, it's very hard to understand for me. I don't know if we call that.
You're not alone. You're not alone. You're not alone. Nestor, you notice what I did a while ago? I asked you to put up one hand and put up four finger.
Yes, sir.
Because the story not finished yet, you know. My story don't finish yet. And that's why I want to show you. So you have it on your hand at all times. This A is my lower limit, right here, so. This B down here is my upper limit. This one is my index finger, my middle finger, my ring finger, my pinky winky. Between my index and my ring and my middle finger is a trapezoid. So inside, in the middle of them two first fingers there is a trapezoid. Between the middle finger and the ring finger is a second trapezoid. And between the ring finger and the pinky winky is my third trapezoid. So I have three trapezoids here. But look how many values I have down here. One value here, then two, then three, then four. Watch this. One term separated by an operation. Two terms separated by an operation. Three terms separated by an operation. Four terms. Index finger, middle finger. This plus sign is a trapezoid. No, the book's not going to show you like this, you know. And me know I show you how me want to teach you if you don't understand it. This is my middle finger to my ring finger, the second trapezoid. My ring finger to my pinky winky, my third trapezoid. What's the point, sir? You see them plus signs here are representing the number of trapezoids. Them plus sign here, you're not going to see it explained like this in one textbook. Trust me. The numbers, them signs here are representing my trapezoids. All right? It's not finished yet. These here are called ordinals. O-R-D-I-N-A-L-S. They are called ordinals. My ordinals will be one more than the trapezoids. My ordinals will be one more than the trapezoids. Put up back your hand again and put up back the four finger. How many fingers do you have up?
Four.
How many trapezoids?
Three.
All right. I'm not saying this again, you know. And one time you're going to say it. We're not going to say it one more time, just for emphasis. But we're not going to say it after this. My ordinals will be one more than my trapezoids. Because when I have my four fingers up, each finger is an ordinal. Each finger is an ordinal. Between fingers is what where I'll have my trapezoids. If I have four ordinals, I'm going to have three trapezoids. What if I have seven ordinals? How many trapezoids I have? Six. The ordinals is one more than my trapezoids. Tell me, say that.
Yes, sir.
Sure.
Good. the explanation done. We can't find nothing more to talk about it. It's done. We have 22 minutes. Allow me to just work this question with you, and then you can see what is happening. All right? Let's go. I don't want anybody to blink. Let's go. Numero uno. It says use trapezoidal rule to estimate all of them something here. G's on P, sir, start. Sir, we can't just go ahead and integrate it, sir. No, because the man say use trapezoidal rule. So if you go and integrate this normally and say x cubed over 3 minus 3x, and you put in your upper limit and lower limit, and you get your actual answer, you're wrong. You get 0 mark. Because the man them said to you, say, use trapezoidal rule. So we have to go use trapezoidal rule. See here? It tells you, remember, n represents the number of what? Say trapezoids.
Number of trapezoids.
So n represents the number of trapezoids. So if I have 3 trapezoids, how many ordinals do I have?
4.
Good. Very good. So you catch it. So this is what I'm going to have. So I know I'm going to have 4 ordinals, right? So I'm going to have f of 0, then f of 1, then f of 2, then f to the n. I mean, I could call this 3, right? I could call this 3. And let me change it and put my...
I forgot to put the 3 man.
Leave your don't touch. All right, so let's go now. So remember, the first thing that I need to do is to evaluate the width of my trapezoids. Because, I have the upper bound and the lower bound. And the question tells me how many trapezoids I'm supposed to have. So therefore, each trapezoid is supposed to be equidistant to the other one. Mathematics. All right? So look at what we're going to be doing now. We're going to say delta x is going to be b minus a. B is the upper limit, so it's going to be 2 minus a negative 1 over the number of trapezoids, which n is equal to 3. 2 minus 1 is 1. 2 minus 1 is going to be 3. That becomes 2 plus 1, which is 3, and 3 over 3 is 1. So this tells the width of the trapezoid. So each trapezoid is going to have a width of 1. Each trapezoid is going to have a width of 1. Sir, what do you mean by that? Start counting with me. Put up your first finger and call it -1. After -1, which number comes next?
0.
Very good, 0. And after 0, which one comes next? Which is the next ordinal? Let me use the terminology. Which is the next ordinal?
1,
And after that ordinal, which is the next?
2, which is the upper limit.
Very good. I reach upper limit. So how many ordinals do you now have?
4.
Excellent. Excellent. So I'm recalling my equation. Now look at what is happening. We're not integrating, We are approximating. We're not integrating. So we know what our ordinals are. Oh, Lord and Father of all mankind. So ORDI, my ordinal is going to be -1, 0, 1, and 2. My ordinals are going to be -1, 0, 1, and 2. Now, if you look at, what I will do is double check. Where I have my commas will tell me how many trapezoids. Because remember, the trapezoids is in between. It comes in between the something. All right. So this is 1 trapezoid, 2 trapezoid, good, 3 trapezoids. I'm on the right track. All right. And then now, look at what is going to happen. See my function here, the original question right here. So remember, we're not doing the question. We're not integrate. Sorry, we're doing the question, but we're not integrating. We are approximating. So in my function, every time I see a x, I am going to substitute my ordinal in the function. So for the first ordinal, which is going to be -1, see it right here. So -1, I'm going to say negative. Anywhere in f of x, I see x, I put -1. So f of -1 is going to be -1 squares minus 3. And negative 1 squares is going to be positive 1. And positive 1 minus 3 is negative 2. That done. I move on to my next ordinal, which is 0. Anywhere in f of x, I see x, I put 0. So f of 0 is going to be 0 squared minus 3, which results in a negative 3. My next ordinal is 1. In the function, anywhere in f of x, I see x, I'm substituting 1. See it right here, so 1 squares minus 3, 1 squares is 1, 1 minus 3 is going to be equal to negative 2. My final ordinal is going to be 2. Anywhere in f of x, I see x, I put 2. So f of 2 is going to be 2 squares minus 3. 2 squares is 4. 4 minus 3 is going to be negative, positive 1. So watch me now. Watch me and watch me carefully. You see them number I'm having in blue? Look at what I'm going to be. Remember now? Remember, my upper limit and my lower limit will not be multiplied by 2. My upper limit, my lower limit will not be multiplied by 2. So watch me. This negative 2, oh crap, I leave out something. I'm going to come back to it. I'm going to come back to it. No, let me just do this first. Remember, the formula says delta x over 2, don't it? And so we have delta x here, we calculate delta x to be 1. So we have to put this 1 now over 2. Can you see that?
Yes, sir. Yes, sir.
And that explains this 1/2 you see right here. So let me go again. Don't take the piece of chicken out of your mouth and pay attention. My delta x is right here, so that I calculated. Remember, delta x tells me the width of the trapezoid. The trapezoids must be equidistant from each other. All right? Now, when I get my delta x, when I get the value of delta x, I will always divide it by 2. Every time, sir, yesterday, today, and always. You'll always divide it by 2. All right? So that explains this 1/2. The first value is not affected by the multiple. Why, sir? Because only one base it have. It don't have no base to the left of it for multiply. But the one you have to the left and to the right, the one you have to the left and to the right, the one you only have to the left, it don't have nothing to the right. So therefore, this negative 2 for the first ordinal is going to remain as negative 2. My second ordinal is going to be multiplied by 2. 2 times negative 3. So is my third ordinal, 2 times negative 2. But my final ordinal not going to be multiplied by no 2. It's just going to remain as it is. I don't need a parenthesis right there. Let me just fix it up. OCD. All right. So I'm going to have this one right here. No, it finished because I substitute into the formula. I'm just going to evaluate it. This half is this half. This negative 2 is this negative 2. 2 times negative 3 is negative 6. 2 times negative 2 is negative 4. And this one is this one. Negative 2 minus 6 is negative 8. Negative 8 minus 4 is negative 12. Negative 12 plus 1 is negative 11. And a half times negative 11 is going to be negative 11 over 2. And this is going to be my approximation. This is going to be my approximation. And this we get for the answer for the approximation. No, for teaching purposes, I want to prove something to you. Do you all understand what I just did right here?
Yes, sir. Yes,
All
sir.
right. Watch me now. I like proving things to you. So we are going to be doing the actual calculation. And this is a revision. We're doing the actual calculation. And I did allude to the fact earlier that, when we're integrating this, we add 1 to the power divided by the new power. So this is going to become x squared. When I integrate x squared, I'm going to get x cubed over 3. See it right here, so? Hey, it must be love, Your teacher come to class and have them sit down and do all of them calculations for come to class and just come. Oh, may I tell you, make sure you pass the exam here? Real talk. So when I integrate x squared, I'm going to have x cubed over 3. So it now becomes x cubed divided by 3. And when I integrate negative 3, I'm going to get negative 3x. My upper bound is 2, my lower bound is negative 1. So I'm going to have my upper bound minus my lower bound. Look at what happens. Look at what happens. This is going to become 2 cubes over 3 minus 3 times 2 minus negative 1 cubes over 3 minus 3 times negative 1. 2 cubes is 8. 8 over 3 minus 6 is this first bracket. This is going to be negative 1 over 3, negative a third. When I multiply two negative numbers, I get a positive number. And then, you know, the when I work out this one here, I'm going to get negative 10 over 3. You can work out that and show negative 10 over 3. And when I work out this, I'm going to get 8 over 3. I'm going to subtract that, I'm going to get negative 6. Uh-oh, negative 6. But I get negative 5.5. It has to be a real approximation. My actual calculation gave me negative 6. My actual calculation gave me negative 6. But my approximation gave me negative 5.5. So I am off by negative 0.5. Can you see that?
Yes, sir.
All right. Here's my question to you. Why do you think I'm off by negative 0.05? Because of the?
The ordinal, sir.
No, they what?
Or the
The the concave is concave. The
overestimation. Very good.
overestimate.
Right. Not ordinals, but overestimation. So you see that piece here, so?
Sir, wouldn't that be an underestimation?
An underestimation, sorry. Yes, you're correct. An underestimation. My overestimation wasn't enough for my underestimation. All right? My overestimation, thank you. My overestimation right here would not be enough for my underestimation. So therefore, I would have grossly underestimated the stuff by 0.05. Now, let me just stop and just say something to you. You know, any of you, you know, contract somebody to do anything for you. Say, for example, you know, you want somebody to make a bookcase for you or put in a kitchen or add on or bedroom or whatever the situation is. Build a shoe stand for you. You say to the man, here's the plan. How much it can cost? And the man come and say, you know, we put on the extra one room, you know, it could be 200,000 plus the material. And these are the list of materials that I'll need. And the man give you how much what you need, and you go to the place and the man them tell you, say, oi, the material come to $800,000. So you say to yourself, say, all right, 800,000 plus a labor cost of 200,000, that's $1 million. And you say to yourself, say, no, me I go to the bank, we go borrow $1 million. Let me tell you something. That is just a ballpark figure here. It's going to cost you more. Because chances are you're not going to buy all of the material one time. It may so happen that the time you're ready for buy the cement price gone up. And what's like what we are going on with the war and the gas prices? By the time we go back there, so $2 gone on a block because they might wait for a shipment or something to come to make the block them and whatever the situation is. So when you finish, you may end up spending 1.1 or 1.2 million. All right? Because of the underestimation. Now, if the contractor is liberal, he may overestimate and say, you know what, I better me tell him, say, it's going to cost $1.3 million, and then after that, it come out to $1.15 million. So at least, because we know so them are going to go, and this is what a lot of people do. They overestimate, especially when they know that you're not paying it out of pocket, and you have to go to the bank. So they overestimate it and say, here the plan. I am going to put my thing up to $350,000. Me and you have that agreement, say, at $200,000 may I charge you. But I'm going to put my labor cost up to 300,000 or 350,000, so you can get that extra 150 for any miscellaneous, we call it. Same thing like yourself. So when we look at our error, we recognize that this piece is going to be an underestimation, because when it concave down, I underestimate it. When I concave down, I underestimate. When I concave up, and if you look at it, you can see it, you know. The piece here, that gap right in here, so is so great that them little two pieces here, so can compensate for this up here. So this is what my approximation gives, -11/2, and my actual will give me -6. All right, and that will give me my -6. Now, there's some you don't know. There's some you done for the night. You
Sir,
tell me. Yes, honey. Go ahead.
Is this because the last time you told us that definitely critical point will be coming on the finals? Could you tell us that this will be on it too?
I'm if to tell you, it must come on the exam.
Yes, sir. It's Sasha. I can tell you with confidence.
Nice and easy.
Sir, confidence, because I've been looking through the past papers. If you realize, sometimes I drop based on the topic, sir, teacher, drop a picture, and I see trapeze on every paper, every single one of them.
Trapezoidal depend every single paper.
Everything, sir.
Nice and easy. Nice and easy.
You better learn it. And guess what? This is all that I have said to you in terms of ordinals, because let me tell you the trick of the thing. Sometimes the questions say, it don't say n equals 3. It may say 6 ordinals. So if it is 6 ordinals, what is the value of n?
N is
5.
5. Because the ordinals will be one more than the number of trapezoid. Use the fingers to help you. You have 4 fingers, 3 trapezoids. And that's why I start off with this question, so you can use your hand to always remind you. Right, Nesta Poo? You use your hand to always remind you.
Yes, sir.
So you have 4 fingers, 4 ordinals, but you have 3 trapezoids. And this is where the error comes in. Now, if you look at the bottom of this thing, it says calculate the error in using the approximations. Now, oftentimes they'll say calculate the error in whatever. I'm not going to go through that tonight. My aim here is to talk to you about the trapezoidal rule done, It done. My aim is to talk to you about the trapezoidal, explain to you the formulation, explain to you why the first one and the last one is not multiplied by 2, and I showed you a while ago. I demonstrated to you the difference between ordinals and the number of trapezoids. Ordinals are going to be one more than the trapezoids. And you're not actually doing the calculation, you're actually going and substituting the ordinals into the function every single time to get an answer out. You see, like how we get our answers here to be 1 and -1 and then pretty numbers there, sometimes you're going to get fractional forms. Sometimes you'll get fractional forms, but don't worry about it. Just commit yourself to the question, because some nice 10 marks, them something you come to. Some nice 10 marks. And if you can catch your 10 marks out of something and put down that you're good to go, a face-to-face exam. So you need to start studying from now and putting all of these little things into practice. So me get it, and I some me get it, I some me understand it, and I some me teach it. Done me done for the day. Any questions?
Nope, no question.
Have a wonderful rest of the day. Be early for your class, your next class.
Sir.
Be good. Yes, Nestor.
Sir,
Yes, Russ.
may I send you a message now, sir?
Hi, link me, man. Me know the from I see you on YouTube, me know that you talk. Link me, man. Link me, Rush. Come on from me Zoom and link me, man.
When we for call you?
Don't leave me right now. Come and go inhale some food. I don't know why I'm feeling and sounding so nasal, but this only happens when I jump into the pool. When I go swimming, I don't have a pool at my yard. Next thing I go think I have a pool at my yard. It only happens when I
and then we're going to say, we know that you were lounging by the pool.
That's the point, right? And Ryan is not here, and I don't want Ryan to take me on. So when I go to the pool, I sound like this when I go to the pool, but I don't know why it is that I'm sounding so nasal. So I'm gonna inhale some food first and see if this feeling kind of pass by. But guys, trust me, no problem. Trust me, guys. It is not difficult. After your class at 9 o'clock, I really want you to go through again. I'm going to see if I can send you the notes tonight. I want you to go through again, so it is that you can commit this to memory. You understand it now? You can't wait until Thursday, because Thursday I will go over again. All right? Have a wonderful rest of the evening.
No, sir.
Hold on a
Sir,
sec.
I'm gonna ask you a question before you disappear about small change.
Uh-huh.
The formula that you give us, right?
Mm-hmm. Mm-hmm.
You do times h, and the h is usually the difference between, I try to find my bearings, sir. The difference between,
The initial and the increase.
yeah, so sir, what it would it be the same thing where it may not be exactly if we should punch it in the square root of whatever number they give us into the
Absolutely.
calculator, it will be a little just like the
Absolutely.
trapeze one.
Absolutely. Tell me why. There's a big word that we're using because it is an
Approximation.
very good. It is
All right.
an
So I'm just want to
approximation.
make sure it's not a rubbish me I do.
No. So for example, if you look back at the question that we did with the root of 37, and then you do the actual calculation of the root of 37, you may be off by 0.0 something.
Yeah.
Because what we're doing are approximations. You know, the question would have said to you, what about approximation something? You man, the word always in it. So you're not going to get the exact. So in some cases, you may get the exact, but in other cases, you're going to get something that is off because it's an approximation. Good question, good observation. Yeah, man.
Right. One
All right.
in
That's
the
all.
code, sir. I think somebody
man.
that trying to say something to you
Yeah,
before.
sir, when we can
Yes,
call
Raj.
you?
Link me after that. Leave me about 9:30 because somebody will leave at 9 o'clock. So leave me about 9:30.
All right, cool.
All right, that's all.
Yeah, man.
Take care, guys. Yeah, man.